All right, welcome back. Thank you for sticking through it all week. Again, we couldn't be happier that you chose to join us and share this excitement of all this that we've been talking about. So we want to talk about this idea of a generative adversarial network. These things have a generative component and they have an adversarial component. And Yann LeCun, the guy we've been talking about, he's the inventor of convolutional neural networks. You saw that video from '89, him at AT&T doing the handwriting recognition. And he thinks that these are the biggest things out. And he kind of knows what he's doing. So these are models that can generate things. You give them some random noise, and they will generate something that looks just like this real something. And it might be very weird and strange, like a picture of a cat is a very strange mathematical object. But yet this thing will learn how to create these cat-like mathematical objects that are indistinguishable. And so we can generate simple things like handwriting, right? This is what kids have to learn how to do. You have to learn handwriting, first grade kind of thing. How is it that your brain's doing that? And the teacher acts as a discriminator, and they go, that's not a very good 7, it looks like a 1, you gotta do a little bit better. And you get this feedback, and you have this adversary of the teacher providing feedback, and as a student, you're trying to generate more and more convincing letters such that you can pass, the first grade. I don't know how I made it out of there, because somehow they didn't look at my letters. They shouldn't let me out. So what we do is we take real letters. You don't want to use my handwriting. We get someone with decent handwriting. Get a bunch of real characters. And then we're going to feed them into a discriminator. The discriminator is going to get this image, and we're going to say, hey, you're like a neural network. You're like this flower 17 thing we've been talking about. This might be an AlexNet. You're just a regular neural network. And it's going to try to output just basically one number. Is this real or is this fake? Is this a real digit? Do I think this is a digit that came from the actual real world, or do I think it's one of these counterfeits that's generated by this generator? So we kind of have a cat and mouse scenario where these two things are going to fight. This one's going to try to get really good at generating characters that can trick this thing. And this thing's going to try to get better at telling which ones are real and which ones are generated. Once this learns, this thing gets really good at making really convincing digits, and this gets really good at deciding which digits are real. So we kind of have a forgery situation, and then we have real data, right? You maybe think $100 bills or something. You've got counterfeiters, and then you've got the Secret Service that's trying to figure out, is this stuff counterfeit? And then you're gonna send this to the next layer, and you're gonna say, is this a real $100 bill, or I think this is a fake $100 bill? And so this generator, which is generating $100 bills, is going to have to take an input. You have to give it creativity. Where do we get creativity from? Interesting enough, you give this randomness. So this would suggest that somehow randomness is really important for the recipe in creativity, that you have to supply these things with noise, with random numbers. One of the most shocking things that I've come across recently is there's actually a market, there's an open market for random numbers. If you can generate random numbers and you can ship them across the internet a few million a second, there's people who pay a lot of money for these. Oh, these are really good numbers, yeah. You don't want your numbers to repeat, right? You don't want recycled, these are yesterday's random numbers. We've seen these already. You gotta have really good random numbers. And if you have the best random numbers, you can sell this. There's some companies that do some kind of gimmicky things. I don't think they're really for security, but just kind of for fun. And in their lobby, they have a wall of lava lamps. And they point a camera at this wall of lava lamps. And the idea is the lava lamps are kind of all really wacky, probably kind of chaotic. And that when you sample this thing, that you're getting a lot of random input. I don't quite buy it. I would argue that those lava lamps are probably very regular compared to some other processes. Are these real? Are they passing the visual Turing test? Do these look like churches? Does that look like dining rooms? Does that look like kitchens? None of these are real. These are complete fake images. These buildings have never existed. These rooms don't exist. Right? They've never existed anywhere. If you get up close, you'd kind of see that they don't quite make sense. And when you zoom in on them, they kind of start to disappear in terms of oh wait, no, that's not. What is this? What is all this? Okay, that doesn't quite make sense. But from back there, I bet they look really convincing. So this is sort of generating. Another thing you can do with these is you can just try to fix images. Right? So here we have an original image, and then it's been made blurry. And you can see these two different techniques they're comparing here. One is a ResNet, which is like an AlexNet type, and this is a GAN. So this is a generative network. And so this thing has been trying to generate an image that will sort of trick it into thinking this is just the original. And you can see it sort of added details, right? It's very blurry in here. It created details. Are they the same details as this? No, not really. But they're kind of convincing. I mean, it doesn't look unrealistic for like a sort of a scarf type thing. So you can have these things generate faces from low resolution, right? It's like in CGI, they always joke, enhance, enhance, and you get this crazy thing, right? And then they'll get the reflection off their eye and get the license plate, right? Not yet, but maybe sometime soon when you look at this kind of stuff. So here's like a real person's face. Here's when they sort of made it all blocky. This would be sort of the traditional way of doing it. And this is where it can sort of fill it in. And so it has to kind of be creative. It's sort of making up people because it doesn't know. You know, there's lots of people that's consistent with this face, but it kind of looks like the person. So there's a few of these, and I kind of want you to be aware of these, you know, as you go looking at some of the. So we have the sort of the original GAN, and I think it's only maybe like 2.5, maybe 3 years old tops, the whole general space. And then these are the much newer versions. So there's the conditional GAN, the cycle GAN, and the info GAN. And so we'll talk a little bit what these are. So just for the regular GAN, we're going to be taking in images. We're going to be passing them through these convolutional neural networks. It's going to take in our MNIST, our digit. It's going to break it down into features, and then even more features, then even more features, and then finally in the output, we're going to be able to decide not what number it is. We don't care about that right now. We just want to know, is this a real digit? I think this came from the real world, or I think it came from this generator thing. So the really cool thing is you can take these neural networks, right? And this went from a big image all the way down to like a number, right? We can flip this and run it backwards and start with a number and have it create an image. So this is kind of crazy, right? This is something called convolution transpose. Sometimes it goes by deconvolution, which sounds like a good name, but it means something else. So it's a bad name for it. But this is like a really exciting breakthrough in the field to be able to run these things backwards and have it actually output images. You think, well, how does it know, given just a number, how does it know what to make the pixels? Right? Well, these weights will decide. So just like we had weights in here that were collapsing the numbers and reducing them each time, this is going to have weights. They're going to be settings, parameters that we're going to learn, and those are going to learn how to take noise, random noise, like white noise, like shh, like white noise, and turn that into an image. It's kind of crazy, right? When we get creative, does our brain like tap into our noise sensor, and that's where our creativity comes from? We suddenly start listening to noise or something. So this is a slightly different version. This is called conditional GAN. And so sometimes you can say, I want you to make something, but I want to give you a head start. I want you to start with something. And so here's a problem that we sort of invented. What we did is we found a database of textures. Just like a whole bunch of just random sort of photographs of stuff kind of zoomed in, so you get patterns like this. And so think of this as kind of the picture, right? And then what we did is we went to a random spot in this image and we cut out a random shape, and we replaced that area with another random texture, right? So this is just a different random texture, and we sort of cut out and stick that there. A scenario for this might be, you know, you've got a floor cleaning robot, and there's lots of like pattern in this, but we might get some like chewing gum that has to get cleaned up. How in the world is the robot going to know, like, not to scrub the pattern off the thing, right? It's like, oh, here's some marks. I'm just like 25 days later, it's like gone through the floor, right? It's going to have to understand that, like, this is the floor, and then this is the thing I have to clean off it. Or you can imagine like automatic bridge inspection. You could just run a drone under a bridge and look for rust spots and things like that, or up and down the seawalls to look for damage. So we're going to take this generator, and just like before, we're going to give it noise, but we're also going to give it a head start. We're going to say, take this thing, feed it into the generator, and what this thing's going to do is going to take pairs. And so this is a real pair. This is the actual image before. This is what we did to it. We damaged it. And we stick them right next to each other. We say, this is a pair. Do we think this is a real pair? And this looks real, right? This is a real pair. But over here, you can see, I don't know if you've noticed yet, but this is fake. So the computer has actually filled that red in. So the computer found where the blotch was, and it's tried to erase it. And it's figured out the best way to erase it is with this color. So from the back, I don't know if you could tell, but this has actually been sort of in-painted. It's been filled in automatically. So it's sort of an automatic Photoshop, right? This thing, just from this alone, it decided, you know what, I don't like this thing here. Let me kind of get rid of it and erase it and fill it in with more of the background. That's this idea of a conditional GAN. So you can automatically make these pairs. We'll see more of this in a second. The other one that's really exciting, it's kind of a wacky diagram at first, but it's not that crazy. Let's see, do we have the horse one? Let me come back to this picture. This is what we can do with this conditional GAN. We want to generate something given an input. So here, what's really cool is we're going to make these pairs. You have to have a before and an after, and then this thing can learn to map from the before to the after. So we can take a picture like a cat. We can turn it into edges. This is a simple computer technique to do. And then we can ask the computer to go backwards, to fill in that cat. And it actually painted that cat, right? You handed me colored pencils in this. I'm not going to be able to make that, right? And so here you can kind of draw. You can give it like a silly face, right? And you can say, draw this in. And it's kind of horrific, but you know, you can see that it's still kind of neat. Right? It overall gets like the shading and stuff like that kind of right.
The second one was good.
And the second one's really good. Yeah, I thought the animation was flipped. I hoped it would start with that one, but so in this scenario, we have two different sort of major classes of problems with this, where we have paired, where we want to map from one image to another image, but we have them as pairs. We want to be able to fill in the outline. And amazingly, you can do this. You can give it the outline of shoes, and it will learn to do shoes. But what's even really more exciting is this idea of a cycle GAN, which you don't even need to have pairs. And so in this case, it might be hard to see, but these are supposed to be photographs on the left, and these are supposed to be paintings on the right. And the idea, like we saw earlier, you want to map between painting space and photograph space. And so this is a way of using GANs to do style transfer. And you don't have to have them lined up like this case. And so both of these are very powerful, and it just depends on the problem you're trying to solve. So what these things can do is you can give them a bunch of photographs of the winter and a bunch of photographs of the summer, and the network will learn a concept like winterization. Right? It will learn that snow shows up in the mountains, and this stuff's going to get icy. Right? It's going to learn that in the springtime, green stuff's going to come out, and that the snow is going to melt. Now, these are very abstract, high-level concepts, and it never asked to do that. It just learned. It just gave them two sets of photographs, and it tried to build a map between those two sets. Yeah.
Is this essentially how we're getting better quality images on our cameras, on our phone? I mean, where they're taking styles like
sort of. So, like in the new iPhone, there's a portrait mode that uses a neural network to try to cut you out of the scene, and so it's trying to put an outline around the person. And then it can separate the person from the background, and then it can blur the background. That's kind of a technique that normally like fancy photographers would get with their lenses and stuff. And so that's this portrait mode that has a neural network in it. The apps and stuff, I mean, all this kind of stuff is built into all of these top apps now. You know, it's probably built into every major sort of photo sharing app, is you can add these style transfers. So here we can see on the far left, we see these inputs, and then you can give it different styles. So this one photograph, you can make look like any artist you want. Yeah, you know, if you're going to go into art school, you're going to want to keep this in the back of your mind, right? Say you're like, you know, designing packaging for something, right, for the Coca-Cola bottle, and you wanted to advertise the Summer Olympics and such and such. Are you going to pay, you know, $100,000 for a top artist to paint, you know, the Olympic Village as a painting? You're going to take a selfie picture. So this is really cool. You could take Monet's painting and say, you know, what was the if he had been doing this from a photograph, what would the photograph have been? Which is just kind of nutty. And then here, obviously, going to the painting style. You can do really cool stuff like this. So what you can do is you can take some photos like this, and then you can have people hand label the different regions. So you have people put boxes where there's windows, and they'll label the door and all kinds of, you know, the balconies and such like that. And now we can run it backwards. We run it backwards, and we say, I want a building that looks like this, and it makes this. These are not real buildings. They've never existed before. And what's really cool is you can slide this over. It'll make it a new one, and you can kind of do this live, right? You can do this live on the web. Here's one that learns how to turn daytime into nighttime. Here's one that learns how to take maps and make it look like it's overhead aerial photography. Right, so are those the real houses? Is that house actually colored that? Is that what the roof? No, it's hallucinating something that's plausible for this stuff.
But how is that not just like just having like your GPS?
It is. So it was trained. So what you do is you go into Google, and you can get both of these from Google, and you have the input and the output, and then you give this one to the network, and you sort of force it to output that. And in the beginning, it outputs like random noise. And you say, no, I needed this. And so you have lots of real ones. And then this is like an area that it's never actually seen before. So it's just going to kind of just make up stuff that makes it look like this, but it'll put roads and houses accordingly. It's kind of neat. Like it put the green spaces. Like it's hard to see, but there's like a little, you know, green spaces. These look real? They look real. I mean, kind of a little too like cartoony kind of thing. Right? Kind of like if Disney made volcanoes. So here's just some more of these. My favorite is the zebras and the horses. Right? So you take a photograph of zebras, a folder of photographs of zebras, and a folder of photographs of the horses. And obviously you never have like the exact copy, right? How could you, right? You just have these different pairs. And what you're going to try to do, let me jump back to that other graph for a second now. Now what we're going to try to do is we're trying to build a machine that's going to take us from horse space to zebra space, and then also from zebra space to horse space. So how do we do that? So this really cool idea of a cycle loss. And right, Russ, will you help me out for a minute? How do you do the right? How do you do the cha-cha, right? You go forward, right, and then you go backwards, right? And then where have you gone? You've gone nowhere. So if you do something and then you undo that something, you should have gone nowhere, right? And so the idea is if I can take my horse, assuming my network works, right? Assuming my magic machine that takes horses to zebras works, and my machine that takes the other way works, then what I should be able to do is I should be able to take a horse, turn it into a zebra, take that zebra, turn it back into a horse, and what should I get? The exact same thing you started with. So this gives us a way of measuring how well our network is working. This gives us a loss. Now that we have a loss function, we can optimize our network. So we're going to do two other things. We're going to take this thing, we're going to map it from horse to zebra space. We're going to say, hey, wait a minute, stop along the way. Do we think this is a zebra? We have real zebras, right? So we can make a discriminator for zebras. That's what the GANs do. Is they make things that can tell you if this is a convincing zebra. So we stop along the way. Do you think that's a real zebra? Okay, I'm convinced this is a zebra. Now send it back, turn it back into a horse. Am I convinced that's a horse? Check. And am I back to where I started? And so we're going to go from this and then back, and then we're going to measure, okay, how different are we? Because this should be 0. If this thing works, it should have gone back exactly where you started. Or if you started from zebra space and you go to horse and you go back to zebra, those two zebras should be very similar. So you have 3 pieces to this loss function. One, the cycle, to make sure as you go back to where you started. And then you're stopping along the way and saying, am I convinced that's a zebra? And am I convinced that's a horse? And so this is the cycle again. So this is what you can do with this, right? Just kind of doesn't even make any sense.
Oh, man.
Now, other than the fact that the tail's a little too stripy, right?
Yeah.
And the stripes move, right? So there's not like a temporal consistency. So this would be a good area of open research to try to build a GAN that detects sort of temporal inconsistencies. And you want to smooth that out and sort of stabilize that zebra pattern over time.
What was the frame rate for doing this?
They would have done this probably offline, but the cycle GAN, the one we have running upstairs on a regular GPU, it's a Titan GPU. It can do 11 a second, 11 frames a second. Yeah, so that's near real time. Kind of thing. That's really good. Now the amazing thing, right? If this was 10, 15 years ago, we would have been talking about the impossibility of even distinguishing the horse from the background. Right? It was just like this unsolved NP-hard problem of like, well, there's brown pixels here and there's brown pixels of the horse. So how would you ever know that stuff right there is not actually part of the horse? Right? When you go into Photoshop and you click the magic wand, you want to cut out something out of Photoshop and you click it and it gets like all messed up. It includes the palm tree in the background and some of the beach. And you're like, that's not the thing I wanted to click on. Because they don't know yet. And so this kind of thing it's just like out of sight compared to what the world was thinking. People weren't even thinking in these terms, 10 years ago. So we're taking the real image, we're going to switch it to the fake domain, we're going to make sure that's real or not, and then we'll be able to go backwards and make sure that we're back to where we started. So we're going to have real examples, and we're going to have fake pairs. So we have real pairs and fake pairs, right? We have real pairs from the internet. We got these from Google. We're going to send the discriminator. But then our generator is also making pairs of numbers because we give it an input. This is the condition in the conditional GAN. The condition goes through the generator. It generates an output. You put that together with the input. You put this together, and you ask the network, do you think this is a convincing pair? Is this a real pair? And it has real pairs. And so it knows what real pairs look like. So how do we go up in this kind of thing? Right? We were looking at this convolution where we have, imagine the blue is our input, and then we have our mask here in sort of dark, and this gray that's sliding over, and then the output's going to the green. So we're sort of transferring the layers. And if we pad the outside, and we can add zeros to the outside, then our input and outputs is the same. It hasn't changed the size. So sometimes that's what we want. We just want to We don't want to shrink our tensor. We want to just keep it the same to pass it to the next layer. But with classification, we need to shrink numbers because we're going from 10 million from our cell phone image down to one image. Is there a dog in this photo? Yes or no? So this that is what you want to do when you want to go down. Here's one that's going down. So we start with a big image, and by doing this convolution, we've actually ended up with fewer numbers. So for classification, that's a good thing. We're on our way to sort of collapsing it down to one number. But with this generator, we want to go backwards. We want to start with the concept like create me, if I turn this one on, make me a cat. If I turn that one on, make me a dog. If I turn this one on, make me a truck. If I turn that one on, make it a house, right? And now you need to create that house. So how are you going to do that? Well, it's going to take your decision and it's going to multiply it by some numbers. And then that's going to create a larger, now pseudo image. And then if we repeat that process a few times, now we can build this thing up to where it's like a full-size image. When it first runs, this image is going to look like nothing because all these weights are random. All these things work random, so it's not really going to be able to generate an image. But by having a loss function, by doing automatic differentiation, all of these weights will tune themselves such that when this thing runs and look at the final layer, it's outputting cats. It's outputting the volcanoes, as you saw. So this is cool. Some of you can go back and look at later. You don't have to worry about the proof of how this works kind of thing, but this is just pretty neat in terms of how we can think of convolution as a matrix multiply. So, for those of you inclined, go home later this weekend and try to see if you can make sense of this and reproduce it. But what you're going to do is we're going to take a kernel and we sort of put it here, right? This will fit in the first section, multiply it, that'll give us the next number. Then we slide it over one, it fits here, that'll give us that number. Then we can fit it down one, it'll go in this lower left, that gives us that number, and then we put it into the lower right. There's only 4 places this shape will fit inside of that other shape, and so we get 4 numbers as an output. We can take this kernel, these weights, and if we stretch them out as a matrix like this, and you notice they repeat, right? There's W00, there's W00 again, there's W00 again, this is W00 again. This is the idea of weight sharing. That we're recycling our weights. We're going to use these same weights over and over again. But what this is telling us is saying we can take this thing, unpeel it like a vector, take this thing, make it into a matrix, and then just do one matrix multiply. And it gives us the same thing we got with our convolution. So normally we think of sweeping this thing across the image. And intuitively that's what we're doing. But mathematically, what the computer is going to do is this. It'll take this and unpeel it, and now we can run this on a GPU. So the reason why the GPU is cool is because the GPU can do this in one go. GPU will go, and that will just output, right? It doesn't have to loop.
As GPUs get better, does that mean that you'll be able to make this look more realistic?
Absolutely. Absolutely. Yep. And I think this is like what Elon's talking about this morning. Like, what does that mean in 10 years then? Right? You might not be convinced I'm not a robot.
Yeah.
Right? Especially if there was like a weird piece of glass here. You're like, no, you're not allowed to go, like Wizard of Oz style. There's like a barrier here, and you're like, you can't actually go, you can't get that close and stuff. Maybe I am, or, you might not be able to tell. Because what is it that I'm doing now that, you couldn't do with something like this, 10, 12 years from now? So, yeah.
So is it just this restriction from the GPUs, or is it also these TensorFlow programs that work as well?
So what do you mean? What do you mean by those restrictions?
So is the reason that the zebra isn't perfect because ResNet or whatever the copier isn't that good?
I think it's because we need more creative loss functions. So this idea of a cycle GAN is a great head start, but like the stripes were moving. So we need to add another term to that loss function, which somehow maybe measures like the continuity over time. And so that's like kind of the open areas. And so I think as we add more and more terms to that loss function, and in real life, we're trying to optimize things. I'm trying to have a good day. I'm trying to, make sure that you get enough sleep. You're trying to make sure you do this and that. And so we're like optimizing multiple objectives. And so as we add more and more objectives to these things, they'll probably get more and more convincing. Especially as they get more and more feedback, right? Like this current system has no feedback. There's no button that says, I'm not convinced about that one, as a human. Right? So it'd be cool to have some sort of human input that could tell us there's stuff we don't like about that animated zebra so that it can say, okay, hang on, I'll work on that for you. Right? So it can try to trick us, like an active Turing test. So what's so exciting and what's powerful about this technique, you think, well, mathematically, who cares? This is doing the same thing. Well, what makes this so cool is now we can flip this around, and it makes sense if we turn this upside down and make this go this way, and then we multiply it by that, we get this. So what we can do is now this gives us a mathematical technique from taking a small list of numbers and turning it into a larger list of numbers, right? We have to create an image. We have to create an image from just like a setting. So we're going to take a small list of numbers. This might be like 0 because I don't want a cat. It's a 1 because I want a dog. It's a 0 because I don't want a truck, and a 0 because I don't want a house. So this is telling me I'm going to have a dog, and so it's going to have to multiply these numbers. Initially, these are all going to be random. So when you make this thing, it's not going to look like a dog at all. But as this thing tunes all of these weights, we'll be able to go from our choice and build up to an image. You can imagine this doing this a few times, and you can get to larger and larger space. So this is the idea of how you go up in your dimension. So what can you do with this kind of stuff? Well, we were looking, this is like our image, our AlexNet, our regular convolutional neural network. We're going to break it up into 96 features, then 256 features, and so on. Finally, we get out a 1,000-dimensional vector. This is telling us this is a tabby cat. What you could do with this is there's something called a fully convolutional neural network. And what you can do is you take the last sort of output and you can sweep it around and you get the probability, you get a heat map of where in that scene we have a cat. So oftentimes we don't just want a number, we want a whole photo out that's telling us where that thing is found. Or oftentimes we want things like this. We want things segmented. And sometimes you want like the buses, but sometimes you want them actually separated apart. It wasn't that long ago when people talked about doing problems like this is you would take a tiny little patch of the scene and like ask what the center pixel was, and you had to like apply that thing over and over and over again. But now you can actually feed in whole images and get out whole images from these networks. When you drive around a car, you don't pay too much attention to all the sort of photographic level details, right? If you pay attention to like all the drivers around you and their cars and stuff like that, you're going to crash. So you kind of make like a cartoon version of the world. And this is what we want to present to robots. Give them a much simpler world. Like all they need to know this is a bus. They don't need to know like the details and that kind of stuff. And so you want things that can output these whole masks. So give an input, go through these convolutional layers, and then you might want something like a probability of there being a certain object, and you want to know where that is. This is really good for like medical diagnosis. You want to know where these sort of tumors are. And so this is sort of something you want to keep in the back of your mind is this idea of an autoencoder. That we want to take something and squish it to a smaller representation and then build it back up. But when we go back up, sort of give us a different flavor of the image. And so somehow in this compressed version, there was sort of everything you needed to know about people in motorcycles. And then when it builds it back up, it can separate the two. And so this is another view of how that works. We take an image and sort of send it through. This is going to shrink it down so that we kind of understand it. You can think of this first half as trying to build an understanding of this. And the second half is going to generate some stuff. Okay, so this one, this should have been one after the one with the textures. So this is that texture problem, and so you can see here we have the background texture. We've replaced an arbitrary region. It makes up a random location and a random shape, switches it out for another texture, and then we have this as a mask. This is the ground truth here on the right because we made this thing, so we know we used this as the cookie cutter to tell us where to replace the mask. So we have that, and what we've done is we've forced the network to output that. So this is a smudge detector. Right, this is the thing that the Roomba can use to know that that's something, this is bubble gum on the tile floor, and to know to clean it up. And so it sort of did that automatically with the conditional GAN. Then what we can do is we can ask it to go further, and we can say, don't just find it, fix it. So on the right is the original, and here in the middle you can see its attempt at trying to fix it. But we didn't tell it where the damage was. We didn't tell it what the damage looked like. We didn't tell it what the background is or what it's supposed to be. So somehow on its own, it has to sort of look at the whole thing, kind of decide what's the overall texture and pattern, what's the the counterfeit pattern that's not supposed to be here, and then try to fill that in and match it. Obviously, it's not perfect, but it's really on its way. And we didn't really give this that much feedback, right? All we gave it is the before and the after. This is a really fun one that we did a few months ago. There's an amazing phenomenon that every time your heart beats, your face flushes red. We can't see this. It's too small of a change for humans to perceive. But we've been able to set up our camera, and if you point your camera at your forehead and you hold real still, then you can just read your heartbeat off. You just take all the pixels, average them, and it's... And if you look at the average brightness of the pixels of your forehead over time, you get your heartbeat right out of that. So the next challenge is, all right, how do you teach the computer where to look, right? And so what I did is I sort of moved around in front of the webcam for about 1 minute, and then I took a piece of green tape, put it on my forehead, moved around the webcam for about 1 minute, and then I ran the cycle GAN. The cycle GAN learns to find me, add the green, and then learns to take it off again. So now we have a system that 11 times a second can do sort of almost like a backwards green screening and can green screen my forehead. Right? To do this kind of stuff, I can show a picture later. There's rooms in this building that they have tripods and infrared cameras, and you wear a jumpsuit with markers and all this kind of stuff, and it's like, all right, act natural. you're never going to be able to measure human behaviors asking people to be in these weird, strange settings. But maybe I wanted to understand, like, where do people pay attention, right? If students are like this, we want to, somebody was talking about their neck, and everybody goes like this, so the neck muscles. And so we want to do like a pose thing. We want to know how do people throughout the day, carry their head and neck and shoulders kind of stuff. This is a way of measuring that, because we can just as easily put a different color dot here, 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 and here, and everywhere, so that we get a full, sort of a suite of tracked locations. And then kind of just like Fitbit is tracking one spot on your wrist, you could do as many spots as you want from a camera, right, for everybody in the room, all at one time. I might as well just show this while we have this going. So this is a brand new version. This is called the Pose Machine. This is a convolutional neural network that's been trained to recognize head, shoulders, knees, and toes, the fingers, and the emotion expression. This is something that was just flat impossible like 2.5, 3 years ago.
Does it do this in real time? Oh, it does say
Yeah. The idea that you could do this for this many people kind of thing from arbitrary video, you could do this from cell phone video. This is just unthinkable like 2, 3 years ago. Think of how much, human behavioral data that you could capture and quantify. It would just be impossible otherwise. So it wasn't that long ago you sort of had to wear the whole outfit with it. You might have seen it as how they capture the athletes in the video games. They get the actual professional athlete to do like the end zone dance and stuff. They bring him into the studio, have him put these motion capture suits on. And you got to basically do this. It's like, all right, act normal, right? It's just not going to happen, right? It's just not going to happen. And you have to be in a room like this. We'll see if there's a camera. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And these are like, $100,000 camera systems. All right, now you can do it on your cell phone. 11 times a second. Right, that's game changer stuff. So this only took 1 minute of video of me like this and 1 minute of video like that. 2 minutes video total. Right? It took me longer to explain it than it did me to run the experiment. This is a really fun one we've been working on. Some special equipment in the building that we use to measure eye tracking. So some cameras. It's more conventional computer vision technology. There's some cameras that live underneath the monitor, and if you didn't know, you wouldn't even know. You would just look. It looks like a regular screen. But the computer is actually looking where you're looking, and it can look at your eyeballs and know where on the screen you're looking. You can use this like a mouse if you're disabled, but we can use this to measure where people, visual attention. So what you do is take a scene like this and you flash it on the screen for half a second, and your eyes will automatically swing around that scene. You can't help it. And then what the computer will do is it'll measure where people spent their time looking. And so this is a heat map. It's sort of an average of the time of where people spent, where their eyes were actually looking on that scene. But that's actually not a real heat map. This is a fake heat map. So we have lots of real heat maps. So we have lots of photographs. We have lots of humans. We can run them through this machine. We can get their heat maps when they look at real photographs. And then we can run our GAN. And we can generate our conditional GAN. We can say, take this as the condition, and please create me a realistic looking heat map, such that when I present this pair, so the discriminator, the pair says, yes, I think this is a realistic pair of images. We can use this. I was just talking to Reggie, and he was saying that Twitter does autocrop. So when you post a picture, Twitter tries to figure out what's the most interesting area in that thing to crop it out. And you can use this kind of technology to say, maybe we should crop this region. So what's really exciting about all this is that we've been asked by the Max Planck Florida Institute to help them analyze their data. So it's a great honor, and we're super excited about this. Some of the best microscopes in the world are right here at the FAU campus in Jupiter at the Max Planck Institute. And as we were saying, they create like a terabyte of data every 30 minutes or something outrageous. And so they have a problem like this, where this is an electron microscope, something called serial block face scanning electron microscopy. And what they do is they take a small piece of brain tissue. They usually work with fruit flies, right, because they don't complain. And you can take this little piece of brain tissue and you sort of essentially freeze it with plastics and stuff. And then you can take this thing and you shave off nanometers at a time, scan it with an electron microscope, shave off another layer, take a picture again, shave off another layer, and you get this stack. And the resolution of the pixels here is nanometers. Right? So those are nanometer pixels, and you just get an outrageous amount of data. And there's the very simple sort of task of outlining the cell membranes here. So we want to just know where different neurons start and stop. So when we always draw these cool neural network pictures, you see like a neuron by itself and these cool branches going out. It's like a hodgepodge mess, right? Like neurons, they live in this just tumble of stuff. And so they're all just it's almost impossible to sort that out. So we want to have computers to be able to sort these things out, to map them, to just know how we're wired up. We don't know the wiring diagram of even our eyeball, right? Not really, not in its full detail. So we want to kind of wire these things out. So we have to cut these things out. So what you can do is you can have graduate students, cut these things out. But what we were able to do is to build a GAN. And so we take the input data, we have the ground truth, it's been hand labeled, we can present that to the GAN, and then it's able to output a realistic looking cutout. And so we're really excited to apply this to the new microscope data. You can do some really funny things with this stuff, that's like almost like algebraic. Right, so here we have a GAN that's able to create a person with glasses. And then there's a way mathematically to these things input noise, right? You take in noise into these. So you feed in random numbers and they're going to output stuff. So you feed in a bunch of random numbers and they're going to output a bunch of different things. Collect all the ones that made a man with sunglasses. And then you average all the random numbers that went into that one. And that gives you sort of a seed. It gives you the noise that will create this type of scene. And you can do that for each of the different sort of categories. You sort of organize them after the fact. And now you get these numbers that represent these concepts. And now you can do like a subtraction on them. So if you take man with sunglasses, subtract man without sunglasses, add woman without sunglasses, you get woman with sunglasses. This is nutty. Right? That's just nutty. Right? If you think this makes sense, I'll safely call you a liar. Right? This is just some crazy stuff. Right? This is a whole new ballgame. What does this mean? Is this what our brain is doing? Right? Are we doing something like this when we think logically? Like you can picture what I would look like with sunglasses right now. You kind of have an idea what that would be. You can put that idea into your mind.
But doesn't this follow basic math of you could break that into two pictures of man plus glasses minus man?
Oh, but it's not doing the math at that space though.
Well, maybe not
Right.
what we think of math, but similar concepts.
Right. In concept space, it's easy. Add the concept of sunglasses. So there's another one that I just want to mention briefly, this idea of the info GAN. And this is really neat because when we sent this thing noise and it created us a character, a digit, say like the 7 or a 2, we didn't get any choice about what digit it created. This is just going to make one up. So what we can do is say we want to make a selector switch that tells us which thing we want to generate. I want to generate a cat or a dog or this or that. We want to choose which one it generates each time. So it's really simple to do. It's really simple to do. You just add a selector switch. So in addition to giving it a noise, you give it, like I say, a one-hot vector. A vector, say, with 10 things, and only turn on only one of those, and send that into the network. It doesn't know what to do with that in the beginning. But what you do is you have it generate an image, and then with our discriminator, we're going to do two things. One, we're going to do the normal thing. Do we think this is a real image, yes or no? We're also going to force the network to output a second thing. We're going to ask it to output the switch setting. It doesn't know what the switch setting runs. It doesn't actually pass through the network. So it has to look at the image. It has to look at the image and decide that it's a 4 and then fill in the bubble that corresponds to the fourth little bubble. And so by adding this second condition of a little selector switch and then just forcing the network to guess the setting of that selector switch, it will automatically build you that selector switch in a very unsupervised way. Now the first little selector switch might not correspond to the 1, and the second one might not correspond to the 2. Right? They'll be out of order, but it will have used each of those for each of the different kinds. Yeah. Yeah.
Does the selector switch, does the discriminator that has to check the selector switch get trained first? Because otherwise, I can totally see the selector switch just getting encoded into the second pixel. To the
Yeah, it's a really good. Yeah, that's really
passing right through.
Yeah, but then it might not be. But then it knows those are fake images.
Oh.
Right, that's a dead giveaway that this thing came from the GAN. Right? It's a dead giveaway. So what's really neat is, so what we can do is we can add these conditions. So imagine this condition at first is a discrete condition, and we have 10 little squares, and we just turn on one of those and send it in. And then by changing which one we send in, it's going to give us the different digits. Like automatically. We didn't ask it to do that. We didn't ask it to do that. Then what's really neat is if we give it, right, so in a regular GAN, if you don't have that, it's not going to do anything. So you just change this, it doesn't correspond to anything with a regular GAN. Then what's really neat is you can actually give it a second one. So we'll give it a second input condition, but we'll make that one a smoothly varying knob instead. Instead of just like a discrete thing of 1 through 10, we'll give that a number that could say be from -1 to 1. Then when we do that and we change that, this thing on its own in an unsupervised way decides that what you can do with that is that became a sweep parameter. That's a rotation parameter. And so that's an input setting that will tell you how much the output is going to be rotated. If you give it a second one, in this case, it goes from -2 to 2, this one will give you the width. So as you increase this, it'll make the digit wider. This wasn't asked for. It wasn't told to do this. It's just decided that I got some extra room in my input space, and here's some stuff that happens with digits, and here's a cool way of, it's like unsupervised. We didn't ask it to do that. So with normal learning, that these representations might be all kind of scrambled up. But when you ask it to do this info, it will automatically organize these things into these smoothly varying features like the angle or the width. And so I think this is very exciting, this idea of an info GAN. So I just wanted to briefly to mention this. This is how you can use something like a generative network in the context of reinforcement learning. So unfortunately, we have to come back next year, and then we'll talk a lot about reinforcement learning and sequences, long short-term memory networks. But I wanted to introduce this briefly. This is a reinforcement learning. This is the DeepMind, and what they've done is they've made this custom video game. This looks like a state-of-the-art video game. I think that's probably shipped with Windows 95, but the colors wouldn't have been as good. So imagine make the graphics a little wonkier, and that's kind of what Windows 95 games look like. And they've made this homemade game where this little agent, has choices. It can go up, it can go forward, backward, left, or right. And it has to choose its own actions. But the only thing it ever gets feedback is that reward. Like maybe it'll bump into the apple at some point. And so what it's doing is it's going to take that scene and it's going to build it into a convolutional neural network. Here you can see it's broken up into the eight different layers there. So we have 8 feature maps in the first layer. And we've got more features here, and then finally we get to these abstract features. And then what's really neat here is you notice there's like a loop here, right? So this is going to be sort of a temporal network, right? This is going to be recurrent over time. And that's trying to output the value. This value is how good is the situation. If I'm in this situation and I press this button, how good or bad is that, right? Like if you're standing at the edge of the cliff and you want to, and the idea of going forward is like, no, there's very low value in that, right? Then you can imagine the opposite, holding the winning lottery ticket and taking it to the, the convenience store and be like, cash this in, please. Like you get a big reward. All you gotta do is just, hand them that little ticket or whatever, and then you're gonna get a huge reward. So what this is doing is this is using a GAN as an auxiliary task. So we were talking about sort of unsupervised learning, and I was mentioning how, children, they're not getting a whole lot of labels. They have to sort of build models of the world that have general utility. So what they've asked this one to do, and it's actually something we did a few months ago in our little rover car, we give it the frame now, and we ask it to guess, if this is what the world looks like now, and I were to make a left, what do I think the world will look like if I make a left? And so this is another task you can give it. It doesn't actually have anything to do with the direct task. You don't actually need that, per se. But in doing that, in asking the neural network to do this task, you get a better brain for this. In the general problem of trying to predict sort of the future state, depending on your action, this gives you a very rich representation of the world. This forces you to understand the input and output and what you're actually seeing. So this is the reinforcement learning. And so I think this is just really neat how you can add this context of this future state. It's kind of like dreaming into the future and considering its action. Right? You can imagine yourself going into the hallway and you walk down the stairs. You can picture that out, and then you can imagine the consequences of that, and then try to plan accordingly. So I think these generative neural networks are going to be very important in all kinds of different areas. Not just creating photographs of cats. Who needs this? But for something like self-driving, we want to predict. What's the road conditions going to look like? I'm going 65 miles an hour, and there's all this traffic, and the cars are here, and this one has a blinker on, and that's going to do this, and I'm going to shift to the left. What's the future state going to be? And can we use that to help us make an action choice? I want to thank you all so much. I hope you've had as much fun this week as I have. This has been a tremendous experience. I can't thank you enough for being here with us. I'd like to just extend the warm welcome to everyone. Welcome to the lab. I would consider you all now official lab members, right? This is how we do, and we want you to have a project, right? Don't just go and leave and come back. Come back next week, right? We'll be here and say, there was this thing you were talking about, and I really think we could do this for that. That's what we're here for. So please, absolutely take advantage of this opportunity.